Recording is rolling. It is Monday, February 12th. So a bunch of you guys just turned in your Unit 2 Dynamics review quiz. Thanks for that. Get those grades soon. Here's top scientists for the previous quiz. Okay, you guys turned about a week ago. Okay, so awesome job if you're on that list. Okay, and then back on Friday, I did a bunch of challenge questions with you guys for Unit 2. So we're going to go over the solutions to those. You guys have the work return on your desk today. Overall, you guys did pretty good on those, right? Pretty good. It's like, I think 7.5 out of 10 questions on average. You guys got right? Something? Right, so pretty good. If you guys do that well on the active exam, it'd be pretty good shape. And then we're going to start the review for Unit 3 okay, with all those topics. I have a lab lined up for you guys tomorrow, turntable friction. You guys remember those turntables spinning? Right? Suppose you put like a math slug on the turntable, right? And you give it a rotation, spin it faster, faster, faster. At some point, it'll break the static friction slide off. So just to plant this idea now, so you guys are a bit more prepared by the time you get it. Right? How can you figure out what is the coefficient of static friction just by spinning it? Right? You're allowed to use, say, like a roller and a stopwatch. So, all right, so you guys go with what's going on? Okay. Yeah, so all right, so let's look at solutions to the last set of questions I asked you back on Friday. All right, so back on Friday, all right, here we go. We're doing the first question you guys saw. They said there's a block mass 2 kilograms, and they said there was this tension force pulling up with 10 newtons. So what's the acceleration? Now they did not show this weight. Right? So you had to say, well, that would be the second force. Then acceleration is, okay, here's second law of motion, right? Net force on mass. Right? So the difference between those two forces divided by that mass, boom. Right? So you should come up with 5 meters per second squared downward. Okay, so the next question, there's a block sliding up an incline that has friction. So what's the free body diagram? So you got weight, normal force, and friction force like that. Okay? Number 6, a ladder against a wall. The question was which forces are identical, and you have to say the friction force and the normal force from the wall would be identical. Right? Now, in my solution here, I amended this a little bit. I said suppose it's a frictionless wall, so there's no friction on the wall, right? Which in that case, the weight and the normal force on the floor would also be equivalent in magnitude. Right? Now, if there was friction against the wall, then, guys, if there was friction, what would happen to the normal force from the floor? I bet it would decrease a little bit, because if the ladder's trying to like slide like this, right, I bet there would be an upward force here, so it would alleviate a little bit of normal force from the floor, right? Anyway, here's a simplified version of this. Remember that question being asked at University of Florida? It's like, yeah, questions asked, right? And if you want to solve all these forces exactly, you also need torque, right? So there's also a torque application there. Right? So you like pick a pivot point and you figure out exactly what each of those forces can be. There was a question. What's the force that actually propels our runner forward? There's a runner in motion, right? Or you could change the scenario to, let's say there's a car that starts at rest. You put it in drive and start driving forward, okay? And it's the same answer as to what force drives each object forward, right? It's the force of friction by the ground acting on that object, in this case on the runner, on the person, right? Here's the full free body diagram, right? Weight, normal force from the ground, right? And the friction, now there's also a Newton's third law, equal and opposite friction force, the person acting on the ground. So the ground is pushing the person forward, and the person is pushing the entire Earth backward, right? So it's like equal and opposite forces, right? Okay. So the friction force from the ground acting on the person drives the person forward. Okay. What's the minimum equipment you need to determine coefficient of static friction with a block and an adjustable incline? Right? What's the minimum equipment? This is a lab you guys did last semester. Right, here's the full proof of how you can figure out the answer to that question with, well, at the end of this proof, we got coefficient of static friction is tan theta, right? So as you tilt this higher, higher, higher until finally it breaks friction and begins sliding, right? So that would be this friction force would have to be balanced with mg sine theta, right? You do some substitutions, right? And coefficient of static friction ends up being tan theta for that scenario, right? That's a good one to know. And if they asked about coefficient of kinetic friction, then it would still be viewed as tan theta, but it would be a little bit different theta. It would be what angle to keep it sliding down at constant velocity. That's actually the lab you guys did last semester, right? But if you say what's the angle that initially breaks friction, right? Anyway, you only need that angle. Therefore, the only tool you need is a protractor. Right? That's the minimum equipment. Right? There might be some other ways to find coefficient of friction too. So like a right, but yeah, protractor will do the whole thing. Right? Car brakes to stop. The question was, what's the friction force acting on the car to break it to a stop? Right? So I think I would solve this in two parts. They gave you a table of values. They gave you various initial velocities of the car and the corresponding braking distances. That's what they gave you. Right? Now you only needed one set of data. You didn't need the entire table with all three scenarios. You could pick any one of these, and they would all lead to pretty much the same answer. Right? So I would start with a kinematic equation that doesn't mention time. Right? So you can solve for what's the rate the car is slowing down, right, in terms of the given initial speed and stop braking distance. Right? There's the first part. The second part is to switch over to Newton's second law of motion. Say, well, F equals ma. Right? So just take that acceleration, multiply it by the mass of the car. Boom. Right? There's the magnitude of the friction anyway. Boom, just like that. There was this question, what if you have a disc that's tied by a rope against a wall? And they did say that there was zero friction between this disc and the surface, so no friction, so you don't have to worry about that. Right? They gave you the tension and the rope, and they said, what's the weight of the disc, basically, right? Now, if you draw the full free body diagram, there's the full free body diagram right there, see three forces, and notice all the forces balance out because of equilibrium, right? So this tension and the string pulling up to the left, well, it's kind of pulling up kind of to the left, right? So the amount it pulls up has to balance with the weight of the disc down, right? And the amount it pulls to the left has to balance with the normal force from the wall to the right, right? Which they didn't ask you, but I went ahead and just wrote that in here anyway, right? So this is they set up a 5, 12, 13 triangle. That is one of a number of special right triangles, right? 5, 12, 13 triangle, right? So you could say the component pulling up is like 12/13 of the entire tension force, right? And then that has to balance out with the weight. So the weight compared to the tension force is a 12/13 ratio, right? And for that matter, the normal force compared to the tension is a 5/13 ratio, right? Okay, so you can solve for that too. Okay, right. Oh, this one. This one I gave you guys an extra minute because so it's a little more involved mathematically. So there's this block on a level surface, and you pull up at some angle with some tension. Question is, what's the acceleration of the block? Right, what's the acceleration? So I'm going to say that all the forces vertically zero out, and I didn't actually write that down here, but if this was an FRQ, I would write that out and say, oh, all the forces vertically have to zero out, which I guess there's three, or force of force components. I see a normal force up, I see some component of the tension up, and I see the weight down. Right? Now their diagram was not actually drawn exactly to scale, right? But okay. Do you guys see that this normal force up and this tension component up, right, have to balance with the weight down? Right? So mine's a little more to scale, right? And then so hold on to the idea. That's going to be important later. Right. Now, what about? I think it's actually accelerating just horizontally. So I want to care about what's the net force horizontally, and then I'm going to take that net force and divide by the mass. Right. So I got t cosine theta. Say let's go horizontal. Right. Subtract the friction. Okay. So there's the setup. T cosine theta. Right. Say let's accelerate to the right. Friction. Trying to slow it down. Subtract the two. Right. Acting on some mass. This is the acceleration. Right. But what is that friction force? Isn't friction force coefficient of friction times normal force? Right. Maybe coefficient kinetic friction, I could call it, right? Because it's sliding, right? And then what is that normal force? Ooh, well, that normal force is the difference between the weight and t sine theta. So I did that substitution in brackets right here. Boom, and that's the answer. Okay? So a lot of little parts I had to put together. Okay? And then it all tied together with Newton's second law of motion. There was an elevator that was moving upward and slowing down. So you had to recognize that means it's accelerating downward, which means there's a net force downward. And then this is what the free body diagram looks like: weight, tension. Right? And they said which of those forces is bigger, larger magnitude. You say, oh, well, the weight's a large magnitude. 13, object moving west at constant speed. Now, I know you guys got this question not too long ago too. So here do like a little drone or a plane or something, right? Now, moving west at constant speed. Now, constant velocity, that means that the forces have to zero out. So the forces zero out because equilibrium. Now, they told you two of these forces. They said 10 newtons due west, 10 newtons due north. What would the third force be to maintain the scenario? Right? they say, well, there has to be a force that has a downward component of 10 newtons and a rightward component of 10 newtons, or I should say south and east, right? Put that together and you get a southeast vector. See, 10 squared plus 10 squared square root, you get 10 root 2. About 14.1 newtons. There were a few stacks of boxes in an elevator that was accelerating upward. And they said, focus on one of the stacks. I just went ahead and drew that. Right? And they said, what's the force of the bottom box on the top box? Which is maybe a little fancy way to say, what is the normal force acting on the top box? Right? The normal force. Right? So went ahead and drew that. So here's free body diagram on the top box. I got its own weight is acting down, and there's some normal force pushing up. Right, which is the force from the bottom box on the top box. Right? They could have made this bottom box any mass or any weight, and it wouldn't actually change the answer. Could have made it the floor of the elevator, and the answer would still be the same. So I did this whole derivation here. So I'm pretty sure we did this derivation recently. This is normal force in an accelerating elevator. Right? Now, the fact that it's accelerating up, you naturally get this plus sign here. Right? What if this whole thing was accelerating down? What would change in this box to an answer? This would end up being a minus here, right? Now again, if that's enough RQ, make sure that you can derive the whole thing from scratch, right? I guess just reverse these two, right? Or something like that. Right? Yeah. What about this? What if the elevator is moving up at constant speed? If it's moving up at constant speed, what would the answer be? mg. Yeah, right? Because the a would just be 0, right? Right. There was a question. There's this astronaut floating outside the space station. And how do you get back to the space station? Right? The only way to do it is to have some kind of external force. Now, if this astronaut's wearing a jetpack, then that's good because you can run the jetpack and it'll push backward, propel you forward, and that's okay. But the answer choice involves like basically trying to swim through the vacuum of space like you're swimming in a pool of water. But that doesn't work, right? Because there's nothing to push against. Right? So maybe kind of like a third law or a first law scenario. Right? You can never get back to the station. It's just kind of stuck up there. Right. And then there are a couple Atwoods. I think we did 16 and the bell was ringing about them, but I'll do these last two anyway. Okay. So there was this modified Atwood that almost for certain you're going to get that as a question. I don't see how that couldn't come up, right? That scenario right there. Right? They said, what's the acceleration system? Now, I'm going to say a frictionless surface. They didn't say that, but the answer would reflect that. Or they could word it like, what's the maximum acceleration? Right? That would lead to the same thing. Right? So here's how I do it with you guys. Net force on total mass. But this is from a systems point of view, not an individual block, but the whole system. Right? So I'm going to say the hanging weight is providing the external force. So that's where the 2mg comes from. Right? So 2m times g. Right? There's the weight. Right? Now this top mass has its own weight, but there's also a normal force canceling out. So whatever goes away. And the tension, the strain, well, that's just internal to the system. Right? And so what is that net force moving? Well, it's moving 2m plus m. So it's 3m. The m cancels, and acceleration could be 2/3 of gravity. All right. And then the one that we didn't quite get to, but we'll look at it anyways, back to a classic Atwood. The question was, what speed is either the block's moving after some time interval? Right? What speed after some time interval? Well, this is going to be a two-part solution. First, got to figure out what's the acceleration with these given masses. So I did net force on total mass. Right? Hopefully you guys can do this. I mean, you're going to get this question, right? On the AP exam, they are going to ask you this question, right? Always do, right? So here's 30 newtons versus 20 newtons, subtract net force, divided by 3 kilogram plus 2 kilogram, total mass, boom. Accelerates at 2 meters per second squared. Okay? Right, then, if they give you an interval of time and said, how fast is it going? Then you can substitute that right there. This kinematic equation, boom, you got your answer. Right? There's lots of variations on this they could ask too. If they said, how fast is it moving after some distance? Suppose it moves like 40 centimeters. How fast is it moving? Right? You could start this out the same way, and then your next step could be v final squared equals v initial squared plus 2ax, right? Like in terms of distance at a time. Right? Or you could do conservation of energy. Could also get you the same answer. All right, so you guys got those? All right. All right, next thing. Let's do some, well, I got my stack of posters for unit 3 right here. Okay. But here, I'll throw you guys a question. Okay. Question. All right, you guys are writing this in your notes. Who's got a tabletop? All right, you guys draw on a tabletop in your notes. Okay. And let's put a hole right in the middle of the tabletop. Let's call this a frictionless tabletop. Friction less tabletop. Okay. So no friction. Okay. Okay. And let's take some lab weights. Take some lab weights right here. I'll call this guy M sub A, and let's tie that to a string. Goes right through the center. It's hang straight down, and then hang right here. M sub B. Right, so we got mass A and mass B. Right, guys see that? Right. Now if I just let that go, it's gonna that'd be kind of like a modified Atwood situation, right? Where just go down there. Right. But what if I give this thing a little push? Right. Give it like a tangential velocity and speed. Right. Here, a little sidekick. Right. And then it starts orbiting. Right. Now as long as there's no frictional losses, right, it'll just like stay in orbit like that, like forever, right? It'll just go zoom, 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 right? And if I give it see a kick at some speed, it's going to set up with some radial size r, right? So, question, in terms of each of these masses and the radial size, how fast do you have to kick it, right? So, what is v in terms of mass A, mass B, the radial size? Here, I'll throw a gravity field in the mix. That probably matters too, right? Right. I guess if it was a stronger gravity field, you probably have to kick it faster. Ooh, I wonder how. Like if it was 3 times the gravity field, how many times faster do you have to kick it?
Yeah.
Huh?
What do you mean?
Okay, so here, suppose mass A is like 100 grams, mass B is like 500 grams, and this radial size is like 30 centimeters, right? And you give this a push, right? It starts orbiting, right? And this radial size stays a constant 30 centimeters, right? How fast is it going in meters per second for that to happen? Because if it's too slow, it'll just drag to the center. If it goes too fast, it's gonna like fly out, right? It's gonna lift this one, right? But there's some speed there, like to maintain a constant radial size, right? How fast does it have to be? Now, I'm not giving you guys any numbers. I'm just saying solve in terms of variables. Okay. So, here. You guys go ahead. Give you guys a head start. Walk around the room. This would be, I think, a pretty solid FRT. Right? You could be asked that. Yeah, this was also one of your puzzle questions way back in the last semester. Straight out of your college textbook. All right. Okay. Now you guys got a head start. I'll start walking you guys through the solution, but see if you can beat me to the answer. So always stay a couple steps ahead of me. Okay. So I'm thinking back to, here's the first poster gonna kick off this unit. You guys remember this lab you guys did with the 2 Play-Doh canisters and the string and the PVC pipe, right? Winding this around, right? So, okay, well, how fast do you have to swing this around? So, thinking this hanging lab weight, okay, has some weight I'll call M sub B times G, and some upward force that's the tension. So I'll call it F sub T tension. Okay? Now that tension is going to transfer, and that tension is also pulling this block in, F sub T. And it's the same tension force, same tension. There's only one tension in that string. Okay? Right. And that tension force is acting as the centripetal force, I'll call it centripetal force acting on this top block. Right. So I'm going to say, okay, that's ultimately equivalent to the hanging weight down here. So the hanging weight is equivalent to the tension, which is acting as the centripetal force, right? So there's the framework that's going to solve this whole thing, right? If this was an FRQ, it might have that like near the top of the step of list of steps, right? So this hanging weight is equal to, I'll say mv squared on r, but I'm talking about mass A that's actually in that circular motion, right? So that's the one that goes into that equation, right? Like that, right? And then, okay, well now you can solve for whatever you want. What do you got? 1, 2, 3, 4, 5 variables. You guys see 5 different variables, right? So let's see, what is V in terms of all these other things? Okay, solve for that V. Cross multiply R, divide by mass A. So V equals, let's see, I got mass BG. Right. I'm gonna cross multiply R. I'm gonna divide down mass A. And I'm going to take the square root. Boom, there's the answer right there. That's it. That's the whole thing. Just like that. Okay. All right. What about that side question I was thinking is just, what if the gravity field was 3 times as strong? 3 times the gravity field. Guys, if it's 3 times the gravity field, how many times faster do you have to kick it?
9?
Not 9 times.
Or 3?
Yeah, square root of 3. Yeah, it was like 1.7 something. Yeah. So if it's 9 times if it's 3 times the gravity field, yeah, you need like the square root of 3 times as fast, like 1.7 something. All right, guys, good day. All right, how about when you guys did this lab again with the Play-Doh string and the canisters and the PVC pipe? Right. Now I'm showing here a horizontal circle, like this top string being horizontal, which is maybe true for the tabletop, but it wasn't exactly true when you guys did it. Right? Like maybe the string was hanging down by like 5 degrees or something, right? Which didn't really significantly change the answer. Right? You know, all the graphs came out looking nice enough. Right? But more realistically, especially if you used like a top mouse that was heavier, or you swung around kind of slow, or maybe more of a conical pendulum it was like, right? And if you swung around significantly slow enough where it was obviously like a pendulum shape, right? So this string here is not horizontal, right? Okay. You might get like a conical pendulum. Now, this one, I've had you guys solve questions about this. There's some relationship between here, like if there's some lab width here and some length string and right? How fast you have to swing it around, is that going to correspond to like some angle and some radial size, right? There's a lot of little relationships. Now, if AP asks a question about this, they tend to ask conceptual type questions like, here, let's hunt around for some relationships that, yeah, like if I wanted to solve for something, this could be, I bet it would solve sets like some crazy system of equations, right? Which we've kind of done before, right? How about, guys, what is this radial size? Here, I'll say R equals. Now this is for this conical pendulum. Right, right. Here, I'll go ahead and draw out the whole thing. Let's get a fresh page of paper here. Right. Draw along with you guys. Right, go ahead. Since you guys are taking notes here, do a dashed vertical line. Right. Here's my string. Here's some mass. Right. Draw. Okay, there's the orbit right there. Right. Call this theta from the vertical. Call this L. Call this distance maybe R. Okay. Right. And then there's, let's see, some tangential velocity, some speed v that block is moving to, right? Okay, there you go. Okay. How about this? What is right, so let's go around hunt for some relationships. What is this radial size in terms of this L and this theta? What can you guys say? R equals what? Yeah, L sine theta. There you go. Okay. How about, because you guys see a nice right triangle here? Okay. What about in terms of forces? Do you guys think there's some tension in the string? Some tension? Okay. Ooh. Let's draw a free body diagram for this mass. Okay, I'm going to switch to pinky. Draw a free body diagram. I'll give you guys a head start. Okay, what's the free body diagram on that swinging mass? Ooh, okay. All right, let me do a pause right here. Here. All right, we're back here. So did you guys all draw? Got an mg, and we got a F sub t tension force. Right, you guys got? Okay. Guys, which force is bigger, the weight or the tension force? The tension. Right, there's draw a little bit long, right? Right. So it what exactly is that relationship between mg and tension force? Right. How about this? What if I break the tension into components, saying, well, the tension's kind of pulling up and it's kind of pulling in, right? Kind of up and in. Okay. Is this vertical component, does that balance out with the weight down? Okay. Right. And what about this angle right here? Is that angle theta the same as that angle theta? Same thing? Same thing, right? Right. So put together, guys, what's the relationship between the hypotenuse of a right triangle and the leg adjacent to some reference angle?
Is it mg over cosine theta?
Cosine theta? Yeah, that sounds right. Sounds right. Yeah, right. So I'm gonna throw in one more step right there. I'm gonna say mg is equivalent to tension force cosine theta, right? Because this leg of this right triangle is equivalent to mg, and that would be tension cosine theta, right? Therefore, yeah, if you want to solve for the tension force, that would be mg over cosine theta. Yeah, you could do that too. Right. How about? Right. I bet there's some. Let's do centripetal force. Centripetal force. Right. Ooh, could centripetal force be represented by this leg right here? Is that the tension force times sine theta? Right. So Ft sine theta, which it represents the centripetal force. Could that be mv squared over r? Right, so what that would be. Right. And you could like hunt around and start making some substitutions here. So, right, like this r is L sine theta. I could pop that in right there. Could be one substitution. Right. Right. There's this one. Could pop in there. Could be another substitution. Right. So if you're given some number of variables, you could solve for things, but sometimes the math on this one gets kind of tricky depending on what's asked. Right? Okay, guys, right? All right, let's see what we got next. Okay, conical pendulum. Right. Ooh, how about, right, because the first two we just looked at kind of similar to each other, right? Involve like a point mass on a string. What if you have a whole rotating disk that's all solid together, right? Like this O'Neill cylinder up in space, right? Instead of centripetal force, think of it like mv squared over r. Could you do m omega squared times r, right? Right. So, guys, what's the unit for omega? Radians per second, right? Radians per second. How fast that turning radians per second? Okay. All right, you guys get that? No, if you start up here, let's derive one from the other, right? So centripetal force, you're saying is mv squared over r. Right. By the way, just to point it out, the closest thing they give on your AP equations that you're allowed to use during the exam is centripetal acceleration is v squared over r. That's right here, about a third of the way down the page. Okay, so something like that. Okay. But then let's do a substitution. So you're going from a point mass speed to like a whole disk speed, right? Like different parts of this ladder. This guy climbing this ladder, right? His linear speed's changing, but the angular speed's the same everywhere. Okay? So I'm gonna make a substitution for this v. Right? So I'll say centripetal force equals m times something squared over r. Right? What is v in terms of omega? Or I should say omega in terms of v, I guess. That's what I meant to say. V over r, right? Okay, you can go back back and forth. So v equals omega times r. Did I just no, okay, v is omega equals, I'm being silly. Hold on. Scratch that. All right, I meant to do the omega times r. That's what I meant to do. Oops. Omega times r, right? Because that's the same thing, right? Omega times r, right? So omega is v over r. I'm thinking backwards here. Okay, is that all right? Okay, let me write that out cleaner. Centripetal force is m times, right? Instead of v, I'm going to say omega times r. Right. All right. Now, remember, you have to use radians per second for omega, right, to plug into an equation like this. Right? And then that would be m omega squared r squared over r. And then that's how you get m omega squared r. Okay? All right, go back. Okay. So if there's like a rigid rotating disk, that could be helpful. Right? I bet tomorrow, when I give you guys some turntable labs, I give you guys a lab that involves turntables, I say, right? Okay. I bet might be useful to use this version of centripetal force. Right? Right, here's okay, so analogous variables. Okay, so it says that, okay, so time is still time. It's just saying how far in meters, now how far something turned, right, which you could measure in degrees, but stick to radians if you're ever directly multiplying that angle within an equation. Okay. Instead of linear speed meters per second, now we're saying how fast the turntable rotating. It could be omega radians per second, right? Instead of a, now it's alpha. Angular acceleration radians per second squared. Okay, and in the bottom half of this table we saved for like December unit 7. Right? But right now maybe the top half of the table here about. Okay. Okay, here's those connections right here. Right, so got this turntable rotating. Yeah, suppose you put on 1, 2, three Roosevelts. You might compare, what do you care about their linear motion versus their rotational motion? They all have the same rotation motion, identical rotational motion, right? But completely different linear motion. So here's how far is it turned, how fast is it turning, and then the rate it's speeding up or slowing down, rotating, right? But then here's how far it's moved like in a linear distance sense, and how fast like a radar gun speed, right? And then acceleration, tangential acceleration, right? Which is different for all these three guys, right? This guy in the middle gets 0 of everything, because it's like, doesn't matter how it's rotating, just multiply by 0 radius from the center, right? And the further out you go, he's proportionally up there. Okay. All right. Got that. Got some kinematic formulas for you guys. Well, here it is with the units written out. Right. Here's the no training wheels version, right? Just like those kinematic variables, kinematic equations. Right. Now it just applies to a turntable. Okay. Ooh, how about this? The next one I got coming up is a turntable slows to a stop. Okay, let me show you guys the scenario right there. Okay. Turntable slows to a stop. Now let's make 3 graphs. 3 graphs. Okay, so turntable slows to a stop. Okay. Okay, and you guys know what 3 graphs I'm going to draw. It's little tiny graphs here. Let's do theta versus t, omega versus t, and alpha versus t. So theta in radians versus time in seconds. What's omega radians per second versus time in seconds? What's alpha in radians per second squared versus time in seconds? Boom, boom, boom. Right. I'll walk around the room, see who gets those 3 graphs correct. Those 3 graphs for that scenario. Turntable slows to a stop. All right, thanks. Steven got them. I think Max got them. Steve got them. Eli got them. All right. Ooh, pretty close, pretty close. All right. All right. Yeah, okay. And I see some of you guys think if they gave you an extra minute, you get them too. All right. So start with the middle one like you usually do. Well, if it was spinning, then it had some angular velocity. If it's going to a stop, then eventually it goes to 0. Oh, let me throw one more word in here. Uniformly. Uniformly. Slows uniformly. And all that means is that for omega versus t, it's just going to make a straight line like that, right? Instead of being like some crazy curve, right? All right, okay. All right. Then, guys, what does the slope of this represent? Angular acceleration, right? Which is negative and constant. So that means angular acceleration is negative and constant, right? And then how about theta versus t? Right. Now, if it's still if it starts rotating in a positive direction, then okay, it'll keep rotating just slower, slower, slower. So it's picking up more radians at a slower and slower rate. So it kind of curves down. And guys, what shape is that right there? Parabola, parabola. And what is this point right here? Right as it comes to a stop. It's called the what of the parabola? The vertex, vertex right there. It's like upside down parabola. Hey, this is 3 graphs. Oh, you guys got that? Good. All right. Ooh, car turning on a big track. If AP asks you this question, they'll probably again tend to keep it conceptual, like what force is acting as the centripetal force? And the answer to that question would be the horizontal component of the normal force, right? I've seen them ask, I think, that exact question before, and it's about as deep as it goes, right? Now, someday you're a road engineer and you want to figure out exactly how to bank it. Like, what angle do I need to bank a road given some speed limit cars would probably drive in, gravity field of the planet, and this radius of curvature, right? Right, so here, you can kind of put it together. This ends up creating what the equation you need. Just take inverse tan of both sides and got your answer. Okay. So you could turn without friction, even if the road was iced over. This car would pretty well stay on the road with following that equation right there. Ooh, I got a few trivia. So that was fun trivia. That was fun. AP is not going to ask about Coriolis effect, but that's good to know. Okay, ooh, there's some fun trivia. Okay. Then I'll switch over to planetary motion, as it's like another half of this section, right? This unit 3, right? So way back in the day, history, before Newton, this guy Kepler, who was crunching all this astronomical data and came up with these 3 laws of planetary motion. Right? Now, didn't know exactly how to back them up other than just empirical observation. Right? But then Newton comes along, and we got this right here, universal gravitation. Right. So what's the force between 2 objects, like the Earth and the Moon, or 2 asteroids, or a star and a planet? Okay, here you go. So universal gravity constant times 2 mass multiplied together divided by distance squared. There's an inverse square relationship between the force and the distance. Okay, okay, all together. Right. And since AP likes proportion type questions, then might say something like, if you change one of these masses by some factor, how does the force change? Right? Something like that. Here's inverse square law, say as it applies to light, just to get the idea across, because I think that's a really good example there, right? But gravity works the same way. The fact that we live in 3 spatial dimensions, right? If you're like 3 times the distance out, right? It's like 1/9 of the, well, your eyeball would catch 1/9 of the light, or in terms of gravity, catch 1/9 of the force. Okay. How about, I know there was an FRQ sometime back. I need to dig this up and find it. Right, that involves what if there's an astronaut, say, standing on an asteroid of some radius. Let's say here's a asteroid. Here, I'll label this asteroid. It's got some radius r, some fixed radius, right? A little astronaut up here. And he's gonna take a rock and he's gonna throw. So he like finds some rock on the surface of this asteroid and he throws it straight up. Let me measure off some distance here. Say that's about 4, something like that. Well, okay, this won't be exactly the scale, but maybe pretty close. Okay, throws this rock straight up, so down. Okay, and so that the height above the surface of the asteroid is like 3r. Let's say like that. Okay, and then the rock eventually comes back down and lands back on the asteroid. Okay, it's done. Okay. Now I wonder, what is the gravitational force between that rock and that asteroid as a function of distance? Okay, so here, what's the gravitational force? See, like in newtons, if you wanted to quantify it and put numbers on it, as a function of, I'm going to put lowercase r like as in a variable distance. Maybe you could measure some number of meters, quantify, right? And I'll put some special numbers on here. Let's call this capital R. Let's say the rock had some weight at that point. So like here's like the surface weight, right? Boom. So I'll give you guys that point, right? So at the surface of the asteroid, that rock has some weight, right? Now what about when you get to, right, like way out here? And what is the weight of the rock at its highest point compared to at the surface of the asteroid? You guys see where I'm picking an asteroid, right? Like if I picked a planet like Earth, its weight wouldn't change. It'd be basically a flat line for as far as you were able to throw it upward, right? Like with your own arm strength. Right? But on an asteroid, this might look well, not like a flat line. Right? What does it look like? Well, let's get another point on the curve. Who can tell me, before I write anything else down, at the very peak, right here, at the maximum height, what is the rock's weight compared to at the surface? It's not 1/9. It's a little tricky thing here. A little tricky. All right. So suppose the rock weighs like 1 Newton at the surface. Okay. 1 Newton might be like might feel like this, right? Okay. So 1 Newton rock. Okay. You throw it up to a height above the asteroid surface that's 3 times the radius of the asteroid. Right. Well, here the gravitational force is a lot less than it is at the surface. Is how much? 1/9. It's not 1/9 though. 1/16. That's what I'm looking for. Right. So it was a little tricky here. A little bit tricky. Yeah, okay, so yeah, you guys see it now, right? Right. So this distance, notice we're going from the center, not from the surface, right? Is 4r, right? You guys see that? So over on this graph, it goes all the way up to 4r, right? Right? And it's this height change here. That's the 3r that I gave you guys, right? Yeah, they could do something like that. They could say like the height above the surface, and they'd want you to recognize that it's the distance to the center that matters. Right? I've seen them ask questions like that before. Right? And so yeah, so I do mg over 16. That would be this point right here. Right? And then, well, what curve connects those 2 points? Some kind of inverse square relationship, right? Where it would, if this kept going on, it would asymptotically approach 0. Right? There could be a horizontal asymptote there. Okay, you guys got that? All right. Ooh, orbital speed. Orbital speed. Can you guys derive this from scratch? Go ahead. I could see this being a free response question that they would expect you to derive orbital speed. Okay. So you have to spell out every step. How are you going to derive orbital speed? So like there's a satellite orbiting a planet. Okay. And then I have some follow-up questions too, but this might be like part A, derive orbital speed from scratch. All right. I think Alex got a good start. I think some of you guys got a good start. Right. If you get the setup right, you're probably gonna get this right. Orbital speed from scratch. Say like there's a satellite orbiting a planet. Yeah, Alex got it. All right. Yeah, I think Steve's on the right track. Connor's on the right track. Oh, Ada got it. All right. And I may have missed a couple of guys too, and I think some of you guys are getting there. Right. So here's what I'm thinking is, here's some satellite orbiting this planet. Let's put it some distance r from the center. Say on this curved path going around. So there's only one force on that satellite, and it's its own weight. That might be a step they'd ask too in an FRQ. They might say like, draw the free body diagram. And you only draw one force. It's a gravitational force straight towards the center of the planet. So it's on the satellite. Right? Of course, the satellite's also pulling the planet back with an equal opposite force, but don't worry about that one. So I would say that the centripetal force is provided by that gravitational force. Right? And then you substitute in expressions. Okay, remember from that Plato canister and string lab, right? PVC pipe. Had mv squared over r here. And then gravitational force is like gmm on r squared. Maybe the planet has mass big M, the satellite has mass little m, right? Okay, so centripetal force being provided by the gravitational force, the weight, right? Then the mass of the satellite go away. On the r's go away. If you solve for orbitals, now this is orbital speed for a circular orbit. Yeah, gm on r. So like back in the 1950s when a bunch of Soviet scientists, American scientists trying to figure out how do we get a satellite to orbit, say Earth, right? They were all looking at this on their paper. Right? They're saying, all right, what's the mass of the Earth? What's the radial size? How fast do we have to get this thing going? Okay. Right? You guys get there? All right. So here's there it is right there. Boom, boom, boom. 1, 2, 3. Right. Be free response points right there. Right. And there's also an escape speed version that actually goes through conservation of energy that they're not going to ask you. I've never seen them ask that question, but maybe in college, you might see this in college, right? Or you know what else this could connect to is I could ask a question like, what do I want to ask here? Okay. What could be the speed of? Let's go back to this astronaut on this asteroid, right? And he throws up the rock. Right? Do you guys think if I asked you guys what's the speed of the rock at like some location like halfway up or something, right? You could calculate that. Now, if it was on Earth, you could just say, oh, 1/2 mv squared equals mgh, boom, done. But you can't do that for this asteroid because the gravitational field is always changing significantly, right? So you'd have to use some version of like negative gmm on r as your potential energy, right? So it'll be a little trickier to solve. Right? AB's not going to ask that, though. That's how you do that. Right. So here it is. Oh, all one nice page here, right? Gravitational field, orbital speed for circular orbit, escape speed for a rocket. Okay. Then I got, okay, eggshell planet. This is a pretty good, maybe this is maybe a little bit beyond the scope of what they would ask, right? But if you have an eggshell, if you stand inside the eggshell, the gravity field cancels out. Now, it's not true on the outside. On the outside, you can walk around the surface, but once you step inside, right? What's that good for? Mathematically, if you want to say, well, what if you tunnel down to just a regular solid planet? You could treat it as like a series of eggshells and say like everything above you in elevation would cancel out, right? It's one of those mathematical thought processes, right? It's like, okay, well, you think maybe kind of a calculus type thought process. What if I had just a little bit at a time, just a little eggshell at a time? How would that change things? Okay. Got some trivia here. So tides, they're not going to ask about. Lagrange points, they're not going to ask about. All right. So there you go. And yeah, we got about 1 minute to the bell. So here's your start review. Yeah, tomorrow, I'm going to give you guys some turntables and maybe some mass slugs and figure out what's the coefficient of static friction between those two surfaces. Okay. So just to help you guys out a little bit here. Okay. Maybe the first step could be some version of, if this thing's in motion, so it's rotating some omega radians per second, what's the free body diagram on this slug? So I bet I would do something like this. mg, normal force, friction force. I bet I would start out like that, right? Okay. All right. So yeah, that'll be a wrap on today then.